Today, we're diving into the absolute fundamentals. I mean, the stuff that makes up everything around us. We're talking about the states of matter. So let's get right into it and break down how our universe works.
You've seen this a million times, right? You take an ice cube, it melts into water. You boil that water, it turns into steam. It's all the same stuff, just different. But what is actually going on with the tiny, invisible particles that make it all happen? Well, that's the big question we're going to answer today.
So, here's our game plan. We'll start with the basics. What even is matter? Then we'll uncover the secret rules its particles follow, explore the four main states, take a deep dive into how gases behave, and finally, we'll tie it all together.
Okay, first things first. Before we can talk about how matter changes, we kind of need to be on the same page about what it even is.
You know, it's as simple and as mind-blowingly huge as this. Matter is just anything that has mass and takes up space. That's it. So the device you're on right now, the air you're breathing, even the most distant star you can imagine, it's all matter. It is quite literally the stuff the universe is made of. So if everything is matter, what makes a solid rock so different from, say, the steam coming from a kettle? Well, the answer is in this sort of secret rule book that all those tiny particles are following. So let's crack it open.
And here it is, the kinetic theory of matter. It's this beautiful idea that says everything, and I mean everything, is made of tiny particles. And here's the kicker. Those particles are always moving. They're constantly, randomly, just zipping around. This one idea is the key to understanding everything else we're going to talk about.
Okay, so that big theory really just boils down to three simple rules. 1, everything is just a bunch of moving particles. 2, how much energy those particles have is what determines the state. Is it a solid, a liquid, a gas? It's all about energy. And 3, what we feel as temperature, that's really just us measuring how much energy those particles have. So more heat literally just means the particles are moving faster. Simple as that. So now that we have the rulebook, we can finally look at the states themselves. We can see how this one theory explains everything from a chunk of ice all the way to super hot plasma. Now, we usually talk about 3 states of matter in school, right? But there are actually 4 fundamental ones that we're going to cover. You've got your solid, your liquid, your gas, and then the super energized state called plasma. And this chart just lays out the differences perfectly. Think about a solid. It has its own shape, its own volume. That's because its particles are packed in super tight, just kind of vibrating in place. A liquid, on the other hand, keeps its volume but takes the shape of its container. Its particles have a bit more energy so they can slide past each other. And a gas, it has no definite shape or volume. Its particles have so much energy, they're just flying all over the place, filling up whatever space they're in. And that's also why they're so easy to compress. So what's the deal with that 4th state, plasma? Well, this is what happens when you get to insanely high temperatures. We're talking millions of degrees. The energy is so intense that atoms are literally torn apart, stripped of their electrons. You're left with this supercharged soup of positive ions and free electrons. And you know what? It's the most common state of matter in the whole universe because it's what stars are made of. Now here's the cool thing about gases. Because their particles are so energetic and so far apart, their behavior is actually really predictable. So let's zoom in on a couple of the exact laws that let us predict how they're going to act. First up, we've got Boyle's law. It's what we call an inverse relationship. Basically, if you keep the temperature the same and you squeeze a gas, increase the pressure, its volume gets smaller. Squeeze it harder, it takes up less space. It's pretty intuitive, but Boyle was the one who actually nailed down the math. And just check out the data here. This is so cool. When the pressure doubles from 1 to 2 atmospheres, look what happens to the volume. It gets cut precisely in half, from 600 down to 300 milliliters. It's this perfect relationship every single time. And when you graph that, this is what you get, this beautiful, distinct curve. You can see how the volume drops off really fast at first as you add pressure, and then it starts to level out a little. This is the classic signature of Boyle's law. Okay, next we have Charles' law. This time we keep the pressure steady and see what happens between temperature and volume. And this one is a direct relationship. You heat a gas up, its particles start moving faster, they push outwards, and so its volume gets bigger. Now you'll see we use the Kelvin temperature scale here, and that's because it's an absolute scale. 0 Kelvin is absolute 0, no particle motion, which makes the math for these direct relationships work out perfectly. And again, the data just makes it totally clear. Look at that V divided by T column. It's always the same number. It doesn't matter if you're at 600 milliliters and 300 Kelvin or 200 milliliters at 100 Kelvin, that ratio stays constant. That's the proof right there. So what does this one look like on a graph? a perfectly straight line. As the temperature goes up, the volume goes up, right along with it. It just goes to show how predictable these little energetic particles can be. So we've seen how pressure and temperature affect a gas's volume, which leads to the obvious question, what happens when we put it all together?
All right, we've looked at matter, we've looked at particles, we've looked at some specific gas laws. Now it's time to connect all the dots and see that big picture.
And here's where it gets really powerful. We can take Boyle's law, where volume goes down when pressure goes up, and Charles' law, where volume goes up when temperature goes up, and we can actually merge them. What you get is the combined gas law. It's a single, beautiful equation that lets us predict how a gas is going to behave when you change the pressure, volume, and temperature all at the same time. It's a huge deal in science.
And there's one last incredible piece to this whole puzzle, Avogadro's law. It tells us something that's kind of mind-blowing. If you have the same conditions, it doesn't matter what gas you're looking at, a liter of helium will have the exact same number of molecules as a liter of oxygen. This is the idea that connects all these physical laws directly to the actual amount of stuff that's there. It's the bridge.
So what's the big takeaway from all this? The crucial point is, it all comes back to tiny particles in motion. The energy of these particles, how they interact, that's what explains why ice is hard, why water flows, and why stars burn. It's this one simple set of rules governing our incredibly complex universe.
I mean, we've gone from a simple block of ice all the way to the plasma at the heart of a star, and it's all explained by the same basic ideas. It really makes you wonder, doesn't it? If we figured out these four, what other, even crazier states of matter might be out there just waiting for us to find them?